Right, slight change of tack here. I've developed computer software to make precise counts of very small lunar craters at more than 60 locations across the moon. At each location, as many as 100,000 craters have been measured, so more than 20 million craters altogether. The results are very significantly from site to site. So I've created a simulation model to investigate these differences and to try to unravel the moon's recent history. I'm not sure what to do. Okay, this is a map of some of the locations that I've analysed. As you can see, it covers most of the moon, not just the near side, but the far side, and also at high latitudes, both north and south. They're mainly mare sites, mainly lava materials, but there's some highland ones and a number of young Copernican age large craters, which I'll move on to. So the objective of the study is to investigate crater formation and destruction processes and to develop a simulation model that can actually match the crater densities that we discover, and then try and explain the differences between the various sites. And finally, to estimate the ages of some large young craters. Oh, what happened? What did I do? That's the end of my talk. Well, will you get me back? What do I do here? Oh. Right, let's try this again. Right, okay. So what factors affect the counts of very small craters? Well, the formation process is controlled by the production rates of craters of different sizes. The target properties probably result in different results. Possibly there are secondary craters, and possibly latitude and longitude have an effect on the crater densities. And of course, the main factor is the time since the surface was since the location was last resurfaced. Destruction processes are also important. The crater erosion rates are critical, obliteration by larger impacts, blanketing by ejecta from nearby large craters, and the resurfacing processes that appear to be occurring all over the moon. The crater production rates that I'm using for this simulation are based on the densities of craters at Giordano Bruno. I'm going to call it GB. The temporal imaging results give current production rates, and if you apply these rates to GB, you end up with an age for GB of about 14 million years. An age range of 5 to 10 million years for GB has been estimated from counting craters and also by exposure ages of particles from the Lunar 24 site in Mare Crisium. And 8 million year age for GB is implied by the studies of certain lunar meteorites that are thought to have come from GB. For the purpose of this simulation, I'm assuming an age for GB of 10 million years. GB is the largest known large young crater on the moon, and you can see the area studied outlined in a blue square there. The crater size distributions are being plotted in this work as just simple histograms on a log-log plot, rather than the more normal cumulative plots. This is possible because the very large numbers of craters in this size range, from 4 meters up to 50 meters. The plot for GB is strictly linear, between 4 meters and 25 meters. The slope of this plot is, the best fit line is -5. So it's a very strong correlation on a log-log plot. And there's an inverse power law that must exist between crater size and crater diameter. And you'll see at this particular site, there are 45 times more 7-meter craters than there are 15-meter craters. So it's extremely dependent on size. So creating the simulation, I calculate simply a 1 million year crater production rate based on the 10 million year age for GB. And I create an 8,000 by 8,000 pixel canvas at 0.5 meter per pixel. So this canvas is about 16 square kilometers. Then I have a matrix, a sufficiently large matrix to accommodate all the craters across the diameter range. So we can pick the numbers from there. So the crater diameters are then selected from this matrix randomly and then plotted at random locations onto the canvas in 1 million year steps. So after a million years, you won't be able to see this, but a few larger craters and many smaller ones. The smallest size craters are about 3.5 meters in diameter. So after a million years, you really don't get very many craters. After 10, you get a lot more, a few more larger ones. And all the ones formed during that 10 million year period still remain. So if we plot those against the plot that we obtained from GB, there's a good fit, of course, because it'd be a worry if they didn't fit. But this demonstrates that the process seems to work. So I'll say a little bit about crater accumulation. Crater densities initially increase linearly with time in accordance with the production rate for each diameter. But after a certain time, the production rate equals the erosion rate and a steady state situation is reached. For 5-meter craters, this happens after about 40 million years. For 10-meter craters, the steady state is not reached until about 120 million years. And for 15-meter diameter ones, not until 210 million years. 20-meter craters are continuing to increase for 200 million years. So that's crater accumulation. Now, lifetimes of craters are thought to depend on the diameter of the crater raised to a low power. It's more than linear, but it's less than the square of the diameter. About 1.4 is the exponent. And the density of craters formed as they're formed varies significantly depending on what this power is. So for a power of 1.3, the steady state situation, this is for 15-meter diameter craters, is achieved after 110 million years. If it's 1.4, it's not achieved until 150 million years, and so on. So 1.6, you can get an equilibrium concentration of 15-meter craters of about 24 per square kilometer. Crater erosion follows this sort of picture. As the numbers of craters increase with time, some are gradually eroded away and eventually become undetectable. But even the smallest craters, when we're talking 4-meter craters, they last for at least 20 million years. Obliteration accounts for about 40% of the total reduction. This is when a new crater forms on top of an old one and erases it. So after about 40 million years, the total number of craters remaining rises more slowly because only the less numerous larger craters are still accumulating. Now, let's look at an older surface. This is Mare Humboldtianum, which is 55 degrees north. And at this location, there are 5 times more 15-meter diameter craters than at GB, but only 3 times as many 7-meter ones. So the slope between 7 meters and 15 meters is slightly shallower, minus 4.5 as opposed to minus 5. And the 7 meter to 15 meter diameter ratio is also lower. It's only 30 compared to 45. So this confirms that the lifetimes of 7 meter craters are shorter than those of 15 meter ones. And based on this simulation, this site must have been resurfaced only 45 million years ago. Really, really quite recent resurfacing. You can see the line for Jordan Bruno just there. Now let's look at an older site. This is Wargentin, if I've pronounced that correctly, an ancient crater in the Southern Highlands, which has been filled with lava quite deeply. And at this particular crater, there are 6 times more 15 meter diameter craters than at Humboldtianum, but only twice as many 7 meter ones. So the slope is shallower still, only minus 3.1, and a much lower ratio of 7 meter to 15 meter craters. So this implies that this crater or this surface in this crater is much older. So I estimate that the surface of this crater was resurfaced about 400 million years ago. And this gives you an idea of the ranges of dates of a number of Mare that I've sampled. Some very young ones in Tranquillitatis, a really, really old one in Moscoviense, and others in between. You can see that the Lunar Cods 1 site and the Apollo 15 site were resurfaced around 110 million years ago. Now I'm going to look at some young, large craters, Copernican age craters, Tycho and King I'm going to look at in particular. This is a plot for the ejector blanket at Tycho. And you can see that there are 8 times more 15 meter diameter craters here than there are at GB. So that sort of implies an 8 times older age. In fact, the best fit of the simulation to Tycho provides an age of 110 million years, which is very consistent with the erodiogenic age for Tycho. And it also supports the assumed 10 million year age for GB. But the plot for a patch of impact melt at Tycho is very different. The grey ones, they're green, I think they should be, but the green ones are the impact melt results. The ejector blanket results. So on the impact melt, the fit is just as steep as it is at GB, -5. Okay. It goes all the way down to 3.5 meters, which is very strange. The impact melt must be the same age as the crater, so it must be 110 million years. So for a given energy of impact, the simplest explanation is that the craters formed on the solidified impact melt are 30% smaller than those formed on the ejector blanket. And they survive for very much longer. We've got 4 meter diameter craters here that have lasted for 110 million years. This is, not too far. This is the results for King crater. Again, this is an impact melt at King crater, and it's also has a slope of -5. Again, these craters have lasted a very, very long time. A simple calculation suggests that King crater is 460 million years old. And if you look at the ejector blanket on King crater, again, it's 460 million years old. So it's a very good match between those. And in fact, a number of other Copernican age craters have been measured. Dawes is only 25 million years old. Necho 30. Proclus seems to have about the same age as Tycho. Jackson and Aristarchus are about 180 million years. And the impact melts for those 2 craters are very similar. I wanted to say a little bit, if I could, I've got a minute or so, about resurfacing. The process of resurfacing aren't well understood, but are probably related to seismic shaking, I suspect. But that's a lot of discussion required about that. You can see here that in these two examples, Plato and Frigoris, they've been partially resurfaced relatively recently. There are no really young craters formed there. Whereas at the Ranger 6 site, which is very young, you can see a very old, large crater that seems to have survived the resurfacing event. This is an interesting comparison between Mariontale and Morgentin. There are far fewer smaller craters here than you would expect from the simulation. At 5-meter craters, you would expect 1,000 per square kilometer, whereas in fact, what you get about 250. So there's a sort of suggestion here that there's been a partial resurfacing of the smallest craters. This is an opposite situation. This is in the crater Jules Verne, where there appear to be an excess of larger craters. So again, the surface the location was resurfaced, but some of the larger craters appear to have survived. So it's a very complex, really quite a complex situation. So I'll leave you there with the conclusions. The evolution of small crater populations depends on several factors: cratering rates, erosion, obliteration, target properties, and resurfacing ages. And the simulations assuming an age of 10 million years for Giorgio Bruno, demonstrate that a number of Mare sites have been resurfaced within the last 100 million years, probably by seismic shaking. And craters formed on impact melts appear to be about 30% smaller than the equivalent on measurements on the ejecta blanket. And several other young craters appear to be younger than less than 200 million years old. I'll just show you a couple more slides. This is to do with blanketing. I mentioned blanketing before. This is the site of an impact that occurred in 2013, an asteroid impact, which created a 19-meter diameter crater. If you look carefully, if you look at those two arrows, I don't know if you'll be able to see it, they're pointing to two little craters, very small craters. I don't know if you can see that. After the impact, a much better picture really, that's the impact. And those two small craters are just outside the rim, but they're still there. So blanketing in the immediate vicinity of a crater of this size doesn't seem to have a great deal of effect in terms of destruction. You can see the rays emanating from this new crater indicate that the distribution of ejecta is quite widespread. Anyway, I think that's all. That shows you the end. You've seen that already. Okay, thank you.
Any really quick questions in the room? Or was everyone hungry?
Well, that's easy.
Yeah.
Thank you.
Yeah.
Before you can ask you a question, there's a statement in there about no evidence of secondary craters smaller than 5 meters. I mean, I would have thought most of them were smaller.
Well, I don't know how to differentiate a secondary crater, really, but Harry might be able to tell us. But the regions I've selected have not been close to large young craters. So that could have something to do with it. There is one site I've looked at. Even there, there's nothing obvious to suggest that that secondary craters are a significant contribution, but I could be wrong.
Thank you.
Right.